It's great.
Okay, and then like it's three that he's like.
No, my real actually had one like it's literally a physics. There's no logic.
You watch the okay, so there's you've watched
There's no way.
Okay, guys, time to get started. Chemical reaction, Wednesday lab will be down here at 2:30. This is a group report, one report per group. Details are there. If you have questions, please ask. Report due next week when you come to lab. Next week in lab, we'll have to see what we're going to do. We may do reaction, we may do something else. Before you start pre-lab on next week, let's chat about it. Okay. Our last test, I believe, is Friday week, next Friday. Aldol reaction. Aldol reaction, one of the top 10 reactions in organic chemistry. This first one is a symmetrical aldol where it's two of the same molecules. What did we make here? This is actually another example of an alpha-beta carbonyl unsaturated carbonyl compound. Alpha-beta unsaturated carbonyl compound. Have we made such before? Yes, it was last Friday at about 10:40 a.m. and I said I would ask you if you remember this.
Oh, yeah.
Yeah, you did.
I remember that.
You remember saying that?
Yeah.
Alpha beta unsaturated, yes. We made those before by doing an E2 elimination of alpha halogen. We put in a double bond here, yeah? That would be an alpha beta unsaturated carbonyl compound. That's starting with the carbonyl, sort of the backbone in place, and it's a way to put in the double bond. Here it's a much more involved synthesis because it's not just, we're putting all these carbons here too. It's a little bit more complex, although the mechanism is pretty straightforward. But it is an alpha-beta unsaturated carbonyl compound. That's what the aldol reaction gives. Let me do the condensation. Because we did show an intermediate which had the OH there, yeah? And we said that's sort of the aldol product. This is called the aldol condensation product because to get to that you have to lose water. The OH compound has to lose water to put in the double bond. And typically we said that you always do the full condensation and put the double bond in. Okay, let's do some other examples here. Mixed aldol, which is actually more common. This is where you use two different substrates. What were the two substrates? One of them was the enolate carbon, and then the other was the carbonyl. Look at this. What if we take these two? Actually, if you try to react these two together by an aldol reaction, you're going to get a complex mixture of 4 possible products. Why? For example, where are you going to make enolate? We got hydroxide catalyst. Where are you going to make enolate? Well, you can make enolate here, but you can also make enolate here. By the way, the H of an aldehyde is not acidic. Alpha, anion, resonance here. Where are you going to make enolate? Either. There's going to be no selectivity. Okay, well let's just say you were to make it here. Which carbonyl is it going to attack? That carbonyl or another of itself? It's going to attack this carbonyl or it could attack this carbonyl. Which one's it going to attack? Either. There's no selectivity. What if it attacked itself? Which product would you get?
Top left.
That one. What if this attacked this and dehydrated?
Top right.
Which would you get?
Top right.
You get that. Well, what if this anion was formed and that anion attacked this? Which would you get?
Bottom left.
You'd get this. What if that anion attacked itself?
Bottom right. Top.
You get this. Okay? You're going to get a big mixture there. Thus, to get a good yield of a single product, you have to have some reason for selectivity. Let's look at some reasons or some examples. First off, if you're given such a product here, you need to be able to say, okay, what would be the two components to make this by an aldol? What are the two components? You need an enolate carbon, and the enolate carbon is always next door to what? Carbonyl. Or it could be next door to an ester, so that's also a carbonyl, or a cyano. Okay? But then this other carbon was what initially?
An O.
What was this other carbon of the alkene?
That was still.
That was the carbonyl that got attacked.
Yeah.
You can see that better back up here. We can break this here into that plus that. And that's the same molecule. That's what we started with, two of those. Enolate carbon, attack carbonyl, electrons up, and that gave, I'm going to just draw these as phenyl. Attack carbonyl, electrons up. What else is here? A methyl and a phenyl. We made that bond. This picks up an H, right? And so it becomes OH. And that was the aldol, so it's got the alcohol. But then this loses water, H2O. And we put a double bond here. Al, you make anion again, where? Next to carbonyl. And then you expel that there, and you put the double bond in, and you've lost H2O. But that carbon was originally a carbonyl, right? It was originally a carbonyl that got attacked. That's how the OH was there. But when we lose it, so that carbon was originally a carbonyl, and this was an enolate carbon. So if you come down here and you break this apart, we can break this apart. Okay, which carbon is originally the enolate carbon? That's kind of duh. Which one is originally the enolate carbon? Next to carbonyl. There it is, and there's no other substituents there other than the other thing. This is the bonding we're making. This other carbon was originally what? Carbonyl, and it had boom, boom, bonded to it. Now there's an H there. Doesn't that aldehyde look naked? Throw H becomes an aldehyde. But there's your two substrates, which is what we said, this and this. If these two react by an aldol, according to how they react, if this is the enolate and that's a carbonyl, it would give this here. But if this was the enolate and that was the carbonyl, it would give which one? We've already said this, it would give the first one on the bottom. Right? There's that one substrate, enolate, and the bottom was carbonyl. Please make sure you can go backwards and understand where the aldol comes from. Okay, reason for selectivity. This reaction at the top will give a good yield of an aldol product. There's two reasons. One of them, well, the two reasons kind of come together to give you one product. Tell me a reason why that gives a good, more selective outcome. Look at the product. Which carbon was the enolate carbon? Alpha beta unsaturated carbonyl. Enolate carbon next to carbonyl. Here, right? Get this anion formed. Are you going to make enolate with the other one? The other one doesn't have an acidic H. Aldehyde H's aren't acidic. There's no H here. So that's the only place you can make enolate. So that right there cuts the number of products from 4 to 2. Now, this can react with another of itself. That's a ketone, though. Which is more electrophilic, a ketone or an aldehyde? It's electrophilic, hopefully you know what that means. Which one's more electrophilic? Aldehyde, why? Because the ketone has a methyl and the methyl donates. And as it donates, it diminishes the electropositive character of the carbonyl carbon. Aldehydes are more electrophilic. So is this going to react with itself or the aldehyde? Well, you could say, well, that's not a big difference. It actually will react with the aldehyde preferentially. Electrons up, you can keep on doing work towards and you'll eventually get that good yield. And that's a typical, that's a good yielding aldol reaction where you have more selectivity. Okay. Now in the other example, it was a ketone and aldehyde, and we could say, well, the aldehyde is going to be attacked. But you can't get a good yield of that product. We've already recalled this. Another way to make this, how would you do this transformation here? 2 steps. What would you do first? How would you do this transformation here? Final exam, one question, there you go. Two-step process. What would you do first? We just showed this 10 minutes ago.
Strong base.
What would you do?
Treat it with strong base first.
Strong base? Strong base would do what?
Take the H, Jason.
Make anion here?
Yep.
Okay, what do you want to do now?
Water probably.
Water? What would water do to that? I mean, you can make that in water. I mean, it's equilibrium. Water's going to supply proton. How would the anion react with water?
Just fill it back in. Then you have a base condition now. We need like some sort of carbon though.
What do you want to do from here? Trying to put the double bond there.
Oh, we need a carbon.
Anybody?
Attack the next door card. Kick off one of those edges. Kick off.
And do what?
I was saying kick off one of the group. Kick off.
Kick off what group?
I don't even know. I was thinking of something how to come back, but I don't know.
Well, just like we showed 10 minutes ago, I would first react this with maybe bromine and acetic acid. What would that do? Well, alpha brominate. Then I'll come in here with maybe KOT butyl.
Take away an H and then
What would that do?
Take the H and then kick off the group.
Now we have a base and we can come in here and do an E2 elimination, put the double bond in.
Or family final.
Halogenate and then do E2. We showed that 10 minutes ago,
Yeah.
right?
And at 10 point.
Okay? Otherwise, you have to remove two H's, and that's just an oxidation, and it's very hard to remove two H's. Okay? I'm just asking you to recall that, although we recalled it 10 minutes ago. But that's another way. But see here, you already got your carbons already bonded, and you're putting the double bond in essentially. Up there, we're bringing in two larger molecules, doing the aldol, and boom, you get the product through elimination of water. With the OH leaves from the beta carbon. Okay? All right. Intramolecular. Can you do these intramolecular? Yes, you can. You take that. You take this compound right here, treat it with base. It's actually going to be catalyst. We can get an intramolecular reaction to form a ring. Where we're going to make anion at?
At the acidic.
Oh, well, that's the that answer's never wrong. Although I would say at the most acidic position. Okay. I mean, if you answer that, you're always right. But then let's say, okay, what is the most acidic position?
Beta carbon.
Where at?
The one next to the beta one. Right?
Beta one? That's beta.
Or alpha.
I mean,
Alpha.
This alpha.
Beta.
This beta.
No, isn't the other one right? The
Both
alpha.
alpha.
These are both alpha.
Alpha.
And then the one next to it.
Which one's more acidic?
The one on
Actually, they're pretty much the same, although you could argue for
I'm gonna say the one on
slight. They're both the same. Any difference between these two?
No.
No. Any difference between these two?
No.
Forget about that end. Work on this end. If we make anion here, what could that attack?
The carbon.
The carbon.
Carbon with the carbonyl on the other carbon.
Yes. If it attacked here, show the aldol. Aldol condensation. It attacks, then it loses water. What would be the product?
You have 4 member rainbow.
You can think mechanistically. Just do your mechanism. Intermediate, and then boom. It's not one where you can just have a way to just do it. Think mechanistically. Show the product of that reaction right there. After it loses water.
Four sides, there were 5.
For the fourth.
Anybody have it?
Stop.
Huh? Yeah, that's what I got also.
What size ring we making?
Square. I was thinking square.
Oh yeah, because you have to pull.
Who got it right? Huh? Huh? Yeah. Well, we can do mechanistically. What does these arrow movements give? We got, well, that's a 4-membered ring, if you see that. Inlet carbon attack carbonyl, making this bond. Carbonyl electrons up to oxygen, yeah. There's also a methyl there. So this is the bond we just made with this arrow movement. Electrons onto oxygen. Okay. What happens mechanistically? This picks up an H. I'm not going to redraw it. Picks up an H, right? And then you keep going. Then you make an anion again. Where are you going to make an anion at? Next to carbonyl.
Yeah.
Okay, there's one H there. We remove it. And then what's the last thing?
Take this.
You move in here and you kick off the OH. Right? Very fast step. Forming the anion is the slow step. Kicking it off is a fast step. Okay, we can do this. Anytime you make a pi bond with a lone pair, it's easy to do. We're not doing E1 or E2. And when you kick it off, what do you get? You get that over there. Also, if you think backwards, remember the alpha beta unsaturated carbonyl, you break this too. This was originally what? Enolate. That was originally what? Carbonyl. So if you break it apart and say, I'm going to break it apart, that's enolate, this is carbonyl, and it's got a methyl. And if you do that, that's what we started with. Okay, so that's a 4-membered ring. What if we had made anion over here and attacked? Show that product. What would that product look like? What size ring would that be?
6.
You've moved it over 2 carbons. So it should be a 6.
Well, this here would give, it's actually a 6. 1, 2, 3, 4, 5, 6. Carbonyl is actually going to be in the ring here. Here's the carbon attack. We will make this bond. It attacked electrons onto oxygen. There's also a methyl on there. That used to be carbonyl, double bonded, but this came in, electrons onto oxygen. 1, 2, 3 carbons between carbonyls. That's right. This picks up H from water to reform hydroxide. Hydroxide then takes this H to make anion. This anion then comes in here and expels hydroxide to give product. Plus hydroxide reformed. Hydroxide's catalyst. We have lost water. We form this. An oxygen's gone. Compared to that, 2 H's are gone. So 2 H's and O are gone. This is water.
Wouldn't the methyl be ortho to the ketone though?
Here?
Yeah.
I mean, how? I mean, this came from one, two, three. Carbonyl, methyl. This methyl, or that one, I mean, either way, it's the same thing. This attacks here, electrons here. This is this. There's no methyl on that carbon.
Yeah, I see it now. I see
That's
it.
the carbon. This used to be carbonyl. The carbonyl had the methyl that we attacked. Again, also, if you break this apart, which was the original enolate carbon, top or bottom? The one next to carbonyl was the original enolate. Okay? So this breaks down into a carbon. There's nothing on the carbon other than H's. I mean, it's going to pick up H's to go neutral, to go backwards. And so it just goes back to a methyl. But this becomes carbonyl as you go back. So that we regenerate the carbonyl if we go backwards. Here, that's a 6-membered ring. Okay, which do you think is going to be preferred, the 4 or the 6?
6.
Right, the 6-membered ring. Now this is connected here, right? Yes. This is all in equilibrium. I mean, you make both. The reaction could go this way, but this is going to be more difficult to make the 4-membered ring. So the equilibrium is going to favor going this way. And ultimately, this is going to be highly favored of the 4-membered ring. And such a product can be readily made by just treating this with a little base. It'll close on itself and eliminate water. With the 6-membered ring being preferred. But you need to be able to show the aldol products, aldol condensation products. How about the one below? Show the major product here, the preferred major product of this reaction below. We've been using hydroxide as catalyst. You can also use methoxide or ethoxide. Any O-anion can be catalyst. You can also use amines as catalyst for aldehydes, like triethylamine or pyrrolidine or something.
Yep.
There you go. Show major product of that reaction there. Does somebody have it already?
Actually, sorry, I have it running up. This would be like this on the side. Yeah, there you go. Yeah. Oh yeah. It's got the ring attached.
What size rings could we potentially make here?
5 or 7.
5 and 7. Yes. It's ultimately symmetrical molecule. This end's the same. Forget about that end. You can make anion here or there. It's the same result. Anion here, attack there. That's a 7-membered ring. Anion here, attack here. That's a 5-membered ring. Which is preferred? 5. Okay. This anion here. These electrons attack here. Electrons there. That is a 5-membered ring. Boom, boom, boom. We say, I came this way. Okay. Making this bond. Enolate attack carbonyl, so electrons to the oxygen. What else was on the carbonyl? A methyl. So we made this bond here. This picks up H. We remake anion, and then anion comes in here and expels hydroxide to give final condensation product. It's a 5-membered ring. Ketone coming off, double bond here. Don't forget the methyl. That's a 5. 5-membered ring. There you go. That's going to be favored over the 7-membered ring.
It's getting taken off, but it's not just leaving.
7-membered ring is not favored. Why?
But it's really hard to draw.
5 and 6, boom. Okay. All right. Pretend this arm is longer. Make that, instead of making that longer, I'm gonna make this shorter. Okay. Now let's try to slap hands. Oh, I'm trying to slap hands, but bigger ring is harder for all that to come together. Okay. 5 and 6 is easier to just come together. Because for this to react here, this has to actually, all this has to rotate. You got to rotate all this. And all that rotation requires certain type of conformation, and you're restricting your entropy. Because you got to get it to all rotate over here and bond, as opposed to flapping all over there. Question?
So you said the 5-member ring is favored because it's smaller?
Well, in organic 1 we covered. We said the best rings were 5 and 6, and we discussed it.
Is it because of like stability?
5 and 6 are just best size ring, balance of no less ring strain. 3 and 4 are going to have ring strain. Bigger rings have more of this entropy that they have to overcome. And as it flops around, it's like boom. Like to make a bigger ring is just, that's really not that I don't think the main point. The bigger point is the bigger the ring, the more you have to get all these bonds just right. And that is really going against entropy. And so it's not entropically favored to get all these. And so the transition state is never going to be as achieved. But I don't know that that's the right argument, because ultimately that's a kinetic effect to me. Once you make it, you might say, well, why would it want to break apart and go the other way? Also, if you look at it, larger rings do have, the bond angles like 109.5 may be preferred. Small ring, tighter bond angle. Larger ring actually requires bigger bond angle. And bigger bond angle is also not good. So you don't, I reckon you could call that ring strain, but it's not because the bond is too sharp, it's because it's too obtuse. Okay, so those are some examples of intramolecular aldol reactions. Going backwards, shows how the following can be made using an aldol reaction. Let's do the two in the middle, because this one looks quite familiar. You guys on the right, do the second one here. You guys on the left, do the third one. What are the starting materials? These are all alpha, beta, unsaturated carbonyl compounds, can be made by an aldol reaction. What's the starting materials? This one here is actually sort of a little bit simpler because it's only one starting material. What is the starting material? Yes. You need two equivalents. Get that to react with itself to give that product up there. Because, break this apart, which one's going to be originally enolate? Left or right? One next to carbonyl, left. So that's enolate, there it is. The one on the right is originally what? Carbonyl. And if you make that a carbonyl over there, that's cyclohexanone. That's also this. How about that one over there? Yeah. Would be that plus these two could react. Top carbon would be enolate carbon with no other substituents other than what's already there. So we end up with two H's there to get back to there. Bottom carbon, carbonyl. There's one H there. There it is drawn in. We make it a carbonyl. And so we have two H's and O. H2O is back on the board now. This is actually an example of one of these compounds. That's going to be particularly acidic. Which is more acidic, left or right? They're both alpha to carbonyl, but one's more acidic than the other. That's more acidic because it's between both the carbonyl and the nitrile. So that's why you're going to have selectivity there. It'd be selected for there. Also, your double bond is conjugated with both the carbonyl and the nitrile. That's close to superglue, although it's different, but it's getting close to superglue. That's only handout. How about this guy over here, intramolecular? This will be one molecule. I mean, this was one molecule, but it required two different molecules of this. One molecule, but it reacted intermolecularly. This is one molecule, but it's going to react intramolecularly. And it's going to be boom, 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 double bond, and boom, phenyl. This carbon was enolate next to carbonyl. This carbon was what? Carbonyl. Enolate attacks carbonyl, loss of water, put in the double bond, there you go. Now this could potentially cyclize another way. We could have potentially had this carbon attack this carbonyl. 1, 2, 3, 4, 5, 6. Get another 6-member bond. But since we're going backwards, we don't really have to worry about that on the record. Okay, those are aldol reactions. Before we move on, let's look at, hopefully I have it here. I don't have it. Don't look at the white pages, the one you printed yourself. We'll look at that on Friday. We'll look at that on Friday.
No.
We're going to look at a couple of those there, including the synthesis of Vioxx. Also, in the Klein textbook, there's an interesting application of this. You know that meat from older animals tends to be tougher. The reason for it is because of cross-linking of collagen in the meat, meaty tissue, by an aldol reaction. Makes the meat of older animals tougher. Take a look at that. Cross-linking is bonding, and all that bonding makes it tougher to break apart, even on the macro level. Okay, next reaction, Claisen condensation. Claisen condensation, we actually go back to acid derivatives. So we're going to mix acid derivatives, enolate chemistry all together. Got a ester. We take this ester, treat it with base, followed by H+ workup. We'll have to say why we can get such a compound here. This is really nothing but just enolate doing acid derivative chemistry, attacking the ester. We make this bond here. Base. Where's base going to make anion? Right here. Okay, you can do that far. Methoxide. Note that we're using methoxide base. Why? Keep it consistent with that in case it attacks carbonyl. Okay. What can this attack? Well, it can attack another of itself. Once we recognize this is a nucleophile, then we're just doing acid derivative chemistry that we could have done a month ago. Nucleophile comes in, electrons up. What does this give? Boom, boom, boom. Electrons up to give minus. O-methyl. Now, don't write this, but I could have just said nucleophile, and we did that a month ago. Nucleophile adding to carbonyl. But the nucleophile is this big old thing. It's the big old enolate anion. It's just big. You just have to take time to make sure you draw it right. I mean, so what is the nucleophile? It's the carbon. And the carbon has this here and this here. We made that bond. You got to make sure you get this right. Look at it. And there's the anion there. The anion is now bonded to carbonyl. Electrons up. Now, what's the fate of this anion up here? Is it just going to sit there and we have to protonate it, or
Nope.
can it do something here?
Double bond, kick double bond.
Go reform and kick this off. We're doing acid derivative chemistry. What does that arrow movement give? And you may say, well, the old question, well, don't we have to protonate that first? No, you do not. We're reforming pi bond here with a lone pair. Fast step. What does that give? Boom, boom, boom. Reform carbonyl. Attack. Bonded to carbonyl is now that nucleophile. We just replaced the O-methyl with the nucleophile. So now, but the nucleophile is the enolate, which looks like that. We just made that bond by an acyl substitution, like we did a month ago. Well, that's the product, just drawn differently. It's there. I mean, here the nucleophile is on top. The whole thing, the nucleophile, specifically that carbon, we replace the OME on this carbonyl.
The bond is just a bond. It's split.
Okay, this is not the end of the reaction though, because we got this H here. First off, come back over here. How do we make this anion?
By taking H from with the OME.
Methoxide took an H to give the anion plus what? Plus methanol.
That was the first.
And that's the first methanol we made. Okay, that's number one. Where was the second methanol we made?
After the OME.
When it kicks off.
This OME gets kicked off, so over here we say we get this plus what when that OME gets kicked off? OME minus.
So that takes that.
This is not the end of the first step because that's a base.
So that H
This H, how acidic is that H?
Pretty acidic.
Pretty acidic what?
Because of
is the two.
It's between both. This is a fairly acidic H. It's about pK about 10 to 12. This guy is going to take the H, leave the electrons behind. That plus methanol. And that's our second methanol that we made. We make two. This is in step one.
and then H
That's in step one. What is going to put the H back on before we go to step two? Anything?
Nope.
Is it going to take it from methanol?
No.
No. This is an equilibrium. But which side's favored? Well, how do you judge that?
PKA.
This guy is about 10 to 12. Let's say 10. Methanol is 16. Which side's favored? This side by 1,000,000. That's where it sits at the end. 1,000,000. That means it's 99.99% this and only a trace amount of that. It's negligible. It's really nothing. It's this. There's no other proton source that's acidic enough. What's the purpose of the H plus workup? Well, hopefully you see. What's your favorite? This typically implies strong acid. It could be water, but in this case, water would not be strong enough to protonate that. You actually need a strong acid to protonate it. What's your favorite strong acid? Maybe ACl. You throw in some ACl, that will protonate it. ACl will protonate any anion. And so you have to have an H plus workup here if you want to put that proton on. Because we made it under basic conditions. That's a pretty acidic proton. It ain't going to be there under basic conditions. Question, is methoxide a catalyst? Is this a catalyst in this reaction? Did we reform it? No, we did not. We formed methanol. The base takes the H. It's not a catalyst. You actually need a full equivalent, molar amount. It's not a catalyst here. It's not reformed. Because this doesn't take the H back. It's not basic enough to take the H back. This is called a Claisen condensation. We did condense out methanol. Whenever you make a small molecule that's a liquid, it's called a condensation reaction, even though it wasn't water. Because if you do this at a certain temperature, methanol will distill out, condense out. Claisen. This is a symmetrical Claisen because we use, it's like a dimerization. We use the same molecule to attack itself. What type of product did we make? It's a beta-keto ester. There's your ester, alpha, beta. Beta-keto esters, which are hugely important in biochemistry. Claisen condensation gives beta-keto esters. You can also do a mixed Claisen where you have two different molecules. When you do a mixed reaction, you have to have some reason for selectivity. Look at this reaction here. We got these two compounds, we got some base. Where are you going to make enolate? Here again is your chance to see. Throw in the most part.
The most acidic.
At the
most acidic.
Yeah, the most acidic proton is going to be, yeah, we actually said that in organic one when we looked at, okay, what's the most acidic proton? What's the most acidic proton on the board here?
The one in between the cyano and the carbon.
Right there.
Yep. Only.
Well, it's not the only. I mean, this guy has some acidity. There's no carboxylic acid or phenol or anything. It's all the H's are on carbons. Okay.
And attacks that.
What can it attack?
The electron.
Now, you could argue that it might attack another molecule the same. By the way, can it attack this carbonyl here?
Itself?
What do you call that?
Resonance structure.
Resonance. That's always there.
Ta-da.
I mean, that's not a new attack. That phenomenon is always there. It can theoretically attack another the same, but since this is here, let's use it. If we attack here, electrons up, show the product. Ultimate product after H plus workup. Again, we're essentially having enolates do acid derivative chemistry. Enolate is the nucleophile, which we used 6 weeks ago. We used other nucleophiles. Or 4 weeks ago. That's it. There's our product. Now highlight the bond we made. This used to be an ester. Used to be under my hand was the O-ethyl. But the enolate replaced the O-ethyl by an acyl substitution reaction. Additional elimination. And we have a beta-keto ester now. How'd we do on that? By the way, just to summarize, I know you guys always look back and you say, okay, what really went on here? When the enolate attacks an aldehyde or ketone, what does that lead to? What type of reaction? When the enolate attacks an aldehyde or ketone, you ultimately are doing a aldol reaction, right? Yep. Okay. When the enolate attacks an ester, we're doing not an aldol, but a Claisen. Because the ester has a leaving group built in. You don't lose the oxygen of the carbonyl, you lose the O-ethyl. Okay? Aldehyde ketones don't have leaving groups, so you have to lose the The oxygen is water. We're doing enolate chemistry, but we're attacking carbonyls. Aldol and Claisen. Now, if you're doing intramolecular Claisen, which you can do, we did intramolecular aldols. And intramolecular Claisen has a certain name. It's called a Dieckmann. All right, a Dieckmann is just an intramolecular version of a Claisen.
Okay.
All right. For example, if you take this here, this diester, treat it with base, what type of product could you envision?
Big old
Big, gigantic ring.
Importantly, get out of the pigeonhole of Claisen. Think final exam, whenever, 6 months from now. Think, what type of reaction could we do? We got methoxide. What could it do? It could add the carbonyl electrons up, back down, kick that off.
Well, it's the same thing.
That's the same thing. So what else could possibly go on here? What other chemistry could you envision? Well, let's move over here and consider enolate chemistry. We can have this acid base make this, yeah? Okay, what could it attack?
Carbonate.
no, they're carbon.
Well,
The far carbonate.
here we go. And now you say, well, this is a possible outcome of this chemistry. Let's show that product. Why don't we'll show this next time on Friday. Please do the couple here. Including on the next page, there's one at the top. Please do all of these. Next time, mainly, we'll be moving on to conjugate Michael addition. Michael addition.